The learning goal for today is to show you how to select the appropriate ARIMA model for a particular set of data. The ARIMA forecasting philosophy is based on three ideas. The first is you start with a general set of forecasting rules, and you've learned a number of those at this point, the different ARIMA models that you've learned, and those that you have learned account for almost all of the situations that you would encounter in business, with the exception of seasonal data, and we'll talk about that later. The second idea is the principle of parsimony, which you've been exposed to before. It basically says there will probably be several different models that will fit the data, and the one you want to choose is the one that has the fewest parameters to estimate, because that's the one that you have the most confidence in doing and making good forecasts in the future. The third is iterative model building, and we'll go into that in more detail, but basically it says when you fit a model to the data, you look at things like the residuals or the errors, you look at the actual versus the forecast, and you use those to help you decide whether or not that model is working properly, and if it's not, what you see will guide you towards selecting another model. Here is that general set of forecasting rules, and what you want to know about each of those is the verbal description that tells in everyday language how the forecast is computed. Very few people know how to do ARIMA modeling, and it's not because it's difficult or counterintuitive, it's because it is always presented in such a mathematical fashion that it's very difficult to understand. So what we're going to do is take a little different approach. You have knowledge of an ARIMA022 model, the double exponential smoothing model, and then all of the other models that we have studied are special cases of that model. And so if you have a spreadsheet, for example, and I'm going to provide you one that has the ARIMA022 model, by changing the values of the two parameters, alpha 1 and alpha 2, you can arrive at all of the other models that we have studied, and you can test each of those on your data very quickly. There's two important ideas. I'm going to talk about the second one first. All of the models that we've learned in this class, or the ones that we've spent any time at all on, are the ones that are adaptive. That means like the random walk or exponential smoothing or whatever. The level of the model changes over time, and that type of model is preferable to a model where you estimate an average and then you use that average to model your data, because in the future, if the average or the level of the data changes, you want to have a model that will adjust to that. The first idea basically says sometimes you'll find that there's more than one model that will fit your data, or so you may have two models and the standard error for those two models is within 5% of each other. Pick the one that has fewer parameters. So if you're choosing between a random walk model and exponential smoothing, pick the random walk model because it doesn't have a parameter to estimate. You're much more confident that the model with the fewer parameters will continue to perform as well in the future as it has on the historic data. And here's just a summary of the models that we have studied so far. And we're going to be biased toward the bottom 5 there, those models that are adaptive. And for each of those models, we've listed the number of parameters that have to be estimated. When you test a particular model on the data that you have, there's several things that you can look at that will help you understand whether or not the model is working very well or not. And that is the chart of the actual versus the forecast, the chart of the residuals or the errors, the autocorrelations of the residuals. You haven't heard that term used before. We're going to be talking about that. and then the range of the alphas. We know those should be between 0 and 1. If the alphas come out to be some crazy number, that would be an indication you have the wrong model. And in fact, my recommendation is that you tell solver to constrain the values of the alpha to be between 0 and 1, and you won't even encounter that particular problem. We'll illustrate each of these ideas with examples. This is looking at the actual versus the forecast. What you're looking for here is when you look at the situation on the left, the actual values tend to exceed the forecast, and the forecast is not responding quickly enough as the actual values trend upward. On the right, you see that the forecast seems to be right in the middle of the actual values and is responding quickly enough as the values trend upward, and that's what you're looking for. You get the same kind of information by looking at the residuals, but it sometimes is a little easier to see. Here we have plotted the residuals, and also we've put limits on it at plus and minus 3 standard errors. And on the left, you can see that most of the residuals, or not most of them, but more than half of them are positive, which means we're consistently under forecasting. On the right, the residuals are averaging around 0. If I am gleaning all of the information that's available in my data, the residuals should be random. In other words, if I have a large positive error in this period, I should be equally likely to have a positive or a negative error in the following period. But if I see that having a high positive error in this period means I'm probably going to have a high positive error in the next period, my forecast could be improved by taking that information into account. The way we measure that is by something called the autocorrelation function. You already know what a correlation coefficient is. Suppose we were to compute the correlation coefficient between the errors and the errors that preceded them by one period. That's called the lag 1 autocorrelation. And then I could correlate the errors with the errors that preceded them by 2 periods. That's the lag 2 autocorrelation, and so forth. And if I have a good model, those autocorrelations should be small, and they should be maybe some of them positive and some of them negative. So look at the situation on the left. Here I have a model where there's a very high correlation between the errors. In other words, if I plot the errors, that means I would have a whole bunch of positive ones in a row probably, and then a whole bunch of negative ones in a row. On the other hand, if I look over on the situation on the right, you see that there's very low autocorrelation at the different lags, and the autocorrelations tend to vary in sign. They're some of them positive and some of them negative. That would be what I would be looking for. But I could have avoided that problem completely if I'd simply told solver the legitimate values of alpha are between 0 and 1, and that's would be my recommendation, that you go ahead and put those constraints in when you optimize your parameters. Even if the value of alpha is in the valid range, but it's close to 1, you should always consider a more simple model. For example, on the left, I have fit an exponential smoothing model. Alpha 1 came out to be 0.84. Then I look at the standard error of 8.28, and then I can say, what if I were to make that 0.84 into a 1, just fix it at 1 so that I have a random walk model? That's more parsimonious. It has 0 parameters to estimate. And I look at the standard error, and it's almost the same as what I had before. There's less than 1% difference there. So in that case, I would go with the random walk model, the one on the right. And here's another example which is even more obvious. You come out with an alpha of 0.96 in an exponential smoothing model. That tells you instantly, just go ahead and use the random walk model.